Ada Lovelace, the prophet of the computer. In the annals of technological history, populated by the names of inventors and engineers, one figure stands apart, not for what she built, but for what she imagined. Her story begins not in a workshop, but in the tumultuous world of romantic poetry, and her legacy ends not in the 19th century, but in the digital age she predicted with stunning clarity. Her name was Augusta Ada King, Countess of Lovelace, but she is remembered simply as Ada Lovelace. The daughter of the infamous poet Lord Byron, she was a mathematician, a visionary, and the author of what is now considered the first computer program. Yet, her greatest contribution was not a set of instructions for a machine, but a revolutionary idea that a computational device could be more than a mere calculator. It could be a tool for creating art, for composing music, and for manipulating any form of human thought that could be expressed in symbols. In the clatter of Victorian industry, she heard the faint future hum of the information age, earning her posthumous title as the prophet of the computer. Ada's origins were a battle between two powerful opposing forces: the unrestrained romanticism of her father and the rigid, disciplined rationality of her mother. Just 5 weeks after Ada was born in 1815, her mother, Annabella Milbank, left Lord Byron, terrified that the poet's mad and immoral character would corrupt their child. Annabella, who was herself highly educated in mathematics, a pursuit that had earned her the nickname the Princess of Parallelograms from her husband, dedicated herself to stamping out any potential poetic or emotional excess in her daughter. She enforced a strict curriculum of mathematics, science, and logic, hoping to ground Ada in a world of facts and reason, as an antidote to the dangerous passions of Byron. This deliberate suppression of one heritage in favor of another created a unique and powerful synthesis within Ada's mind. She would later refer to her approach as poetical science, the ability to see the beauty and imaginative potential hidden within the rigid structures of mathematics. She never knew her father, who left England forever and died in Greece when she was 8. But his legacy of rebellion and grand vision haunted her, compelling her to ask bigger, more daring questions than her contemporaries. The instrument through which her genius would find expression was not of her own making, but was the brainchild of a brilliant and irascible inventor, Charles Babbage. Ada first met Babbage as a 17-year-old debutante, introduced to London's scientific elite by her tutor, the mathematician and astronomer Mary Somerville. Babbage, then Lucasian Professor of Mathematics at Cambridge, the same chair once held by Isaac Newton, was the quintessential eccentric genius. He was famously frustrated with the human errors in the mathematical tables used for navigation, engineering, and finance, and he dreamed of building a machine to calculate them flawlessly. He had designed, and partially built, a machine called the difference engine, a monumental contraption of brass gears and levers, powered by a hand crank, designed to compute polynomial functions. Ada was captivated, but it was Babbage's next, more ambitious concept that would truly ignite her imagination: the analytical engine. Where the difference engine was a calculator, the analytical engine was a computer. It was a conceptual leap of staggering proportions. Babbage's design contained all the fundamental components of a modern, general-purpose computer. It had a mill, which is what we would call a central processing unit, CPU, where calculations were performed. It had a store, or memory, where numbers and intermediate results could be held. It used punched cards for input, an idea Babbage adapted from the jacquard loom, which used cards to weave intricate patterns in silk. Most importantly, it had an architecture that allowed for conditional branching and loops, the ability to make decisions and repeat operations based on the results of previous calculations. The analytical engine was, in essence, a mechanical computer made of brass and steam, waiting only for the language to tell it what to do. The opportunity for Ada to provide that language came in 1842. An Italian engineer, Luigi Menabrea, published a paper in French on the analytical engine, based on lectures Babbage had given in Turin. Ada, now a married woman and mother, undertook to translate Menabrea's paper into English. But she did more than simply translate. She embarked on an act of profound intellectual creation. At Babbage's suggestion, she began to add a series of notes to the paper, expanding and elucidating the concepts. These notes, labeled simply Note A through Note G, ended up being 3 times longer than the original article itself. It is in these notes, particularly Note G, that Ada Lovelace secured her immortality. In her writings, she achieved several revolutionary insights that separated her vision from Babbage's. Babbage, the engineer, was focused on what the machine could do, its capacity for number crunching. Lovelace, the poetical scientist, saw what the machine could be. Her first and most famous leap was to understand that the engine's power lay in its ability to manipulate symbols. She realized that if the fundamental relationships of music or art or logic could be expressed numerically, the engine could act upon them. In what is perhaps the most prophetic passage ever written about computing, she stated, "The analytical engine does not originate anything. It can do whatever we know how to order it to perform. It can follow analysis, but it has no power of anticipating any analytical relations or truths." This is a clear articulation of the principle that computers operate on algorithms, not intuition. But then she pushed further. Supposing, for instance, that the fundamental relations of pitched sounds in the science of harmony and of musical composition were susceptible of such expression and adaptations, the engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. Here, she was describing the potential for computer-generated music and art over a century before it became a reality. The practical proof of her genius is found in Note G. Here, she provided a detailed step-by-step sequence for how the analytical engine could be instructed to compute a specific sequence of numbers, Bernoulli numbers. This sequence, a complex series involving intricate recursive calculations, was far more challenging than the simple arithmetic for which most people used calculating machines. Lovelace's diagram, with its columns for variables, V0, V1, V2, etc., and its meticulously detailed operations, is universally recognized as the first published computer program. She had written the code for a machine that would never be built, creating the blueprint for a new form of language, the language of software. Despite the brilliance of her work, published in 1843 in Richard Taylor's Scientific Memoirs, it was largely forgotten in her own lifetime. The analytical engine remained a dream, its construction thwarted by a lack of funding and the limitations of Victorian engineering. Ada's own life was tragically short. Plagued by illness, likely cervical cancer, and battling a gambling addiction, she died in 1852 at the age of 36, the same age as her father. She was buried, at her request, next to the father she never knew, in the church of St. Mary Magdalene in Hucknall. Her visionary work was buried with her, a mere historical curiosity for the better part of a century. The resurrection of Ada Lovelace began in the 1940s, with the dawn of the modern computer age. Alan Turing, the father of theoretical computer science and artificial intelligence, famously referenced her work in his 1950 paper, Computing Machinery and Intelligence, calling her objections to machine originality Lady Lovelace's objection. As historians delved into the prehistory of computing, her notes were rediscovered and recognized for their extraordinary prescience. In the 1970s, the U.S. Department of Defense named a new programming language, Ada, in her honor, cementing her status as a foundational figure. Today, she is celebrated as a symbol of potential. The potential of women in STEM, the potential of interdisciplinary thinking, and the potential of the human mind to see decades, even centuries, into the future. Ada Lovelace's true legacy, therefore, is not merely a set of instructions for a 19th-century machine. It is the conceptual bridge she built between the industrial and the information ages. She was the first to truly understand that a machine designed for number crunching could become a universal symbol manipulator, a tool for amplifying the human imagination itself. In a world of gears and steam, she saw the ghost of the digital future, a world where machines would not just calculate, but create. She was the prophet who looked upon a drawing of cogs and levers and saw, reflected in its brass, the infinite possibilities of the mind.